One more time. Today we're going to be working with solving logarithms. These ones are going to be just a little bit more intense than what we have done previously. And there's a couple of different strategies that we might have to apply here based on the variation of the question. So notice that in number 10, there's two logarithms. Thankfully, they're both of equal base. When we don't see your base, it's assumed that it is 10. These are called your common logarithms. And if they're on either side and there's only just two of them, that's really great. We don't have to combine them at all. Instead, as long as they are in the equal base, they will end up canceling. The reason why they cancel is when we use your inverse property or your swoop method, they will end up canceling no matter what. So your bases here will cancel with your exponential. And again, please go back and watch the video as to why they cancel the way they do. So we're left with 5x is equal to 2x plus 9. Now we can go ahead and solve for your x value as you would any sort of linear approach. So subtracting 2x, we get 3x is equal to 9. Dividing by 3, we get x is equal to 3. Now to check your solution, it's super important for these logarithms that you check your solution, as long as we don't have any sort of extraneous one. So we have 5 times 3 is equal to log of 2 times 3 plus 9. So we get log of 15 is equal to log, let's see, 6 plus 9. So we get log of 15 is equal to log of 15. And as long as they equal on both sides, you have the right solution. Now let's try it again. Let's see another variation that might be a little similar to that. Would be maybe number 15, 17. I'll do one of those two. Let's do 15. All right, so 15, you again notice that you have logarithms on either side. Again, these are common logs because they have that hidden base of 10. So we get to write the base of 10 on either side to allow them to cancel. And it drops. So we're with 10 minus 4x is equal to 10 minus 3x. So let's go ahead and get your x values alone into one side. So we can do so by subtracting maybe this 10x, adding this, or sorry, this 10, and then adding the 4x to the other side. So we're left with 0 on one side is equal to x on the other. So x is equal to 0. So let's go ahead and check that solution. So you have log of 10 minus 4 times 0 is equal to log of 10 minus 3 times 0. We're left with log of 10 is equal to log of 10, which again, they mean the same thing on either side. So we got the right response. I would try it again with number 17, and I'll show you the answer key here at the very end of this video. So let's take a look at perhaps a variation like 11. So you'll notice that with your logarithms, there's now a few more logarithms. Thankfully, again, they're still with an equal base of all fours. So the next thing we want to do is if you have multiple logarithms on one side, we want to combine them. So if they are subtracted, we talked about in a previous video that when we go ahead and we rewrite it, if we have subtraction between the two, we are actually going to go ahead and divide by them. Because this is doing the subtracting, it's going to come down below. On the other side, we just have one of them. Now again, because they have an equal base, and this time it's a base of 4, we can write a base of 4 on either side, which is going to allow us to cancel. We have 2x plus 1 is equal to x plus 2 over 3. Now let's try and get your 3 out of the denominator. So the easiest way to do that is to multiply 3 on both sides. So you're left with 6x plus 3 is equal to x plus 2. And then you're solving as you would a linear expression. So let's go ahead and subtract x to the other side. We have 5x. Subtract 3 to the other side is negative 1. So x is equal to negative 1 over 5. Now we do not want negative responses as far as this negative solution goes, right? Typically we don't want to see a negative solution. But what's happening is that with these logs on either side, they are actually going to be meeting at particularly at x is equal to -1/5. Because keep in mind, when we're talking about these logarithms, right, a logarithm of, let's just say, base 10 of x, right, that is its parent function. And what we've done to these ones is we have just transformed them. We have shifted them over. So as your variations go, at times we can have that negative solution. If we do see this negative solution, we want to plug it back in and make sure that as your solution goes, we want to make sure that they both equal the same exact thing on either side. Which when we go to solve this, let's see, oops, minus log base 3, we'll see that we get log base 4 of 3/5 is equal to log base 4 of, again, 3/5. So this solution is, in fact, justified for this particular one. Let's try it again with 12. So with 12, the only difference is that we now have an addition sign between your logarithms, and all of your logarithms have the same exact base. So we can go ahead and combine. Instead of dividing here, we actually multiply. So it's the opposite. So when we go to plug it back, when we go to simplify, we're multiplying. So we get x squared plus 6x is equal to log base 8 of 5x plus 12. And now we can go ahead and take the same base on either side. That'll allow us to cancel these logarithms. So we have x squared plus 6x is equal to 5x plus 12. And again, because it's a quadratic, so x squared, we want to get everything to one side and combine your like terms. So we're going to subtract this 5x. So we're left with just a positive x. We'll subtract your 12 to the other side. And then we're going to go ahead and factor. So you get x plus 4 and x minus 3 here is equal to 0. So x is believed to be either -4 or +3. Now, if we have a negative response, this is when we're going to cancel it out and then just double check your positive response by plugging it all the way back into the original. So we have log base 8 of 3 plus log base 8 of 3 plus 6. So we got log 3 plus log 9. So you have log of 3 times 9 is 27. So that's on one side of your logarithm. So we also have log of 5 times 3 plus 12. So you have log of 15 plus log of 12, 15, 12. So it's equal to log of 27. So again, that is your correct response. Let's try it again with the one right next to it. So we see addition. We're going to go ahead and combine. We have ln of 2x minus 1 times x plus 3 is equal to ln of x squared plus x minus 7. So let's go ahead and simplify first. So when we FOIL it out, we get 2x squared. So then 2x times 3, so we get a 6x. And then minus 1, so we get 5x minus 3 is equal to ln x squared minus x minus 7. Now, because they are both in the ln has a secret base of e, so you can take e to both sides to allow us to cancel. We get 2x squared plus 5x minus 3 is equal to x squared plus x minus 7. And let's get your terms to one side. We want to bring over the left hand or right hand side to the left so that we are not dealing with a negative leading coefficient. So we're left with x squared. So we subtract an x squared. We subtract an x. We then add the 7 to 0. So then we can go ahead and factor. So we get x plus 2 and x plus 2. So then x plus 2 squared. So this is where x is now equal to a -2 here. Again, we don't use negative responses, so we have no solution. And we could see that by checking your solutions as well. You'll just notice that when we put in -2, that we will not get the same thing on either side. ln of -4 minus 1 plus ln of -1. So again, you're seeing this negative that is coming up on the inside of your ln function, which we don't want to see. So you have -5 times the -1. So while that does switch it to +5, on the other side, we get ln. It's kind of hard to squeeze it in here. We get, let's see, 4 minus 2 minus 7. So we get that 2 minus 7. So again, a negative response. And that is -5. So we get ln of -5. And you can very clearly see that these do not match. So we have no solution here. Now I'm going to leave the rest for you guys to solve. Again, try to check your solution at each and every turn. And I'll show you the answer key right now.